estimate. For example, if you see in this image, we are having some data, it is sequence 1, okay, and using the least square we have got one estimate, it is x1, okay. So suppose if at the next time if you are having you are getting more observations which we are calling sequence 2, so what should be our objective? Our objective should be like that, I have to get a correction value or anything extra value that I have to add in the previous estimate. So what we can see here in the this image, x2 equal to x1 plus c. If somehow we can compute that c value, then we can think of to compute the x2. Okay. So in the sequential least square, our objective will be to get that value which is c here. Okay. So if we get the value c, we add to x1. X1 is the previous estimate from the previously observed sequence. Then you will get the new estimate which is x2 for the sequence 2. Not for the sequence 2, for all the sequences. Is it clear to everyone?
Yes, sir.
Okay. So first we will see this problem. On the basis of that, we will try to understand the sequential least square method. Okay. So everyone please read this question. It is the height of the station A is given. It is 214.880 meter above the datum. And the standard deviation of an observed height difference means we are here we are observing the height difference. Its standard deviation will be 0.005 under root k, and where k is the length of the level root, means whatever of the distance between 2 points. So if you see in this table, we have the stations here from 2. So from A to number 1 station, the observed height difference is 61.478. And the approximate distance between the A and 1 is 10 kilometer. Similarly, we can see here the observations are means the height difference are measured for the from 1 to 2, from 2 to 3, from 3 to A, from A to 2. So these observed height differences are given here, and their approximate distances are also given here. So using this approximate distance, we can compute the standard deviation, because it is 0.005 under root k, and k is the distance which is given here in this in the last column. Okay, so we have to perform the following tasks. Let's see what are these. So first one is compute the least squares adjusted estimates of the heights of points 1, 2, and 3 and their standard errors. The height of A is fixed. With respect to A, with respect to other stations, we have measured some height differences. Okay. So what now we have to compute on the basis of these observed height differences, we have to compute the adjusted estimates of the heights. Okay, so we have to compute these adjusted estimates of heights and their standard errors. On this is the second question. Now, if at a later date, means after some time, the height difference from 1 to 3 is observed, from this 1 to 3, it is observed later, and it is given minus 8.070 meter, whose length is 22 kilometer. Now you have what you have to do: determine new sets of least squares estimates and standard deviations of points 1, 2, and 3 using sequential parametric least square method. We will see this. What is sequential parameter? It is same whatever observation equation you have learned. We have to just make some changes, and we can understand it. Okay. So first of all, you have 10 minutes, and in this 10 minutes, you have to try to solve the first question. Compute the least squares adjusted estimates of heights of points 1, 2, and 3 and their standard errors. So you have to solve it in the next 10 minutes. And what I can help you is that we have to compute three things. It should be very clear to you. The estimates of heights of points 1, 2, and 3. So if you are using h as a variable, as a symbol, so you have to compute h1 cap, s2 cap, and s3 cap, and their respective standard errors. So now parameter, what you say, the variable matrix or parameter matrix, that is very clear to you. Like you have to compute h1, s2, and s3. Now you have to think of observation matrix. Just simply recall that the final answer, it was like x1 cap equal to n inverse u, n was ATPA, so ATPA inverse ATPL. So we have to compute A, we have to compute P, A is again given, and ATPL. So you have to compute L. So only A, P, and L you have to compute from these observations by making the observation equations. Once you have A, T, and P, you can easily calculate the adjusted estimates of the heights. So in the next 10 minutes, you have to try and you have to get the answer. The question is clear to everyone? Alok, is it clear?
Sir, A part.
Yes.
Yes, sir.
Okay. Any doubt on that? Anyone? If there is no doubt, try to complete this A part only in the next 10 minutes. Okay, sir. So is it done? Praveen,
Yes, sir.
is it done?
No, sir.
Anyone who has done this? Ruchi, Vishal
Yes,
Kumar,
sir.
Haruchi. Have you done that?
No, sir.
Vishal Kumar,
Yes, sir. No, sir.
Sumit,
Sir, formed the matrix, but just finding out the values. Just give me 2 minutes, sir.
okay. So everyone, we have you have 5 minutes now. Okay. So please try to complete that. Then after 5 minutes, we'll discuss how to do that and what would be the answer. Okay. So how many of you have solved that? Anyone? Alok, is it done?
Yes, sir, I have raised my hand.
Mm-hmm.
Yes, sir, I have solved, sir.
Okay. What is the answer?
Sir, for H1 adjusted, it is 173.0225. For H2 adjusted, 175.6510. And for
One second.
H3, yes, sir.
Let me check now. Yes.
Sir, it is my answer is, sir, for H1, H2, H3 as sequentially 173.0225, 175.65, and 209.45.
It is not looking right now because you have to see this. I think I missed
Okay,
it.
sir.
This is from height. A is the height from datum. It is known to you. Okay. So if the distance is given from A to 1, it means H1 minus HA equal to this height difference. Is it clear?
Yes, sir, that only
So,
opposite I have taken.
you have to see this, but again, your answer should not be like this 173 because the difference is 61. And if you are going negative, means 214 minus 61, then it will be around 260, na? 260 to 50. It will be not 160, 150. It will be not. It will not be around 173. Is it clear to you?
Yes, sir.
Either think in this way. Either you will add this height difference to 214 or you will subtract it. Is it clear? This is the height difference between HA and H1. Okay.
Yes, sir, it will be H1 minus HA.
Yes. If it is H1 minus HA, then its height will be around 214 plus 61. Just 1 second.
हाँ ठीक है
Okay. Sorry for that. So now is it clear to you?
Yes, sir.
Either you will add 61 into 14 or you will go for subtraction, isn't it? So its height will be not around 173, it will be around 160. Either it will be added and it will be 273, around 273. Okay. Is there any other student who have got any answer? Alok, Sumit, Ruchi, let's see.
Sir, calculating my matrix, sir.
On paper.
Yes, sir.
Then why I will learn the MATLAB?
Sir, actually, I am facing to write the code. So I am prefer to do on my copy.
Okay. Try to keep do it fast. Praveen, Rahul, what's your status?
यस कर रहे हैं सर.
Bhagat, Alok.
सर नॉर्मल मैट्रिक्स के बाद कैसे करना है?
Sorry, repeat.
सर नॉर्मल मैट्रिक्स के बाद एन के बाद
You have got N?
ATPA के बाद
Mhm.
सर कैसे करना है उसके बाद? नहीं आ रहा.
If you have calculated ATPA, do you have L matrix?
L N
L. It was ATPL, no?
ATPA. अच्छा,
N equal
PL
to ATPA. But the second one, it was X equal to minus N inverse U, isn't it? So N was ATPA, but U was ATPL.
Yes sir. अच्छा, ATP.
If you calculated N, then you can compute N inverse. And if you are having a L matrix, then compute ATPL, then multiply both, you will get the answer.
So it will be very complicated, मतलब.
No.
Copy.
Okay. Let me explain. Everyone, please look at the screen. So let's start solving this question. Okay, first of all, you have to make your observation equation. It is L equal to Fx. Okay, so for our case, L is the observation. Okay, so if you have the L1 observation, difference between you can see here, difference between difference between A and 1.1. So it will be written like this: x1 minus HA equal to L1. Is it clear? and HA is given, height from the datum of HA. So it is there is no error in this. So it is written as it was 214.88. Similarly, let me show you the equation. Yes. So you will write like x1 minus HA. So it is x1 minus HA equal to 61.478, and this is your observation. And for observation, you are using L here. So first observation L1 is equal to x1 minus HA. Second observation L2, it is x2 minus x1. You can see here L2 equal to x2 minus x1. Similarly, third observation L x3 minus x2. You can see here. Similarly for fourth and fifth one. So it will be HA minus x3, but HA is given to 14.88 minus x3. Similarly, here x2 minus 214.88. Is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
So yeah, you can see in these equations also you have to compute x1, x2, and x3. Okay. So once it is done, you have to always think about your main equation. It is x equal to n inverse u. N is ATPA, ATPL. It was u. So you have to always think how I can get A, P, and L. Once I have A, P, and L, I can easily solve this. Okay. So we are doing here step by step. If I ask you what will be the approximate heights, because when you have seen this equation L equal to Fx, you must have seen like we will be going for Jacobian type of matrix. We will be writing F1 x naught if it is nonlinear, F1 x naught plus F1 dash. You have seen equations like this. So for that case, we are computing here the approximated height. So for x1, if I think for x1 what will be the approximated height, you know it is 214.88. You know what is L1. So what we can write, approximated height x1 naught will be 214.88 plus L1. L1 was the observation. Now you are having the x1 dot. So similarly for x1, x2, and x3, we can compute the approximate heights. So, from here, is it clear to everyone?
Yes, sir.
Okay. So now, if you have to see, because we have to know ATPL. From here, we can see L. So we can prepare L from here, from the table also, directly from the table also. But we have to compute the weight matrix also and the design matrix also. We can see about the residuals, what would be the misclosure, because we are having approximate heights. So we can directly think about misclosure, because to this equation L1 equal to F1x, what we write, L plus V equal to AX. So for that case, if you wanna see the residual part, so we have approximate height. Okay, we have the observation. So if we put these approximate heights and we use these observations, we can directly see what are the misclosure. For first, second, third, means for L1, L2, and L3, it is 0. For fourth and fifth, it is 0.016, 0.007. So we have computed here the, you can say residual, initial residual, whatever you want, you can say. From these matrix, if you wanna see what will be the design matrix, so we can see because x, the parameters are x1, x2, and x3. So this line is for x1, this is for x2, this is for x3. So whenever you are making the design matrix, we can see the variable is only x1 here, not x2 and not x3 for the L1. For L2, it is x2 minus x1. So x2 minus x1, because x1, x2 will be here once we are writing the equation. L equal to ax plus b kind of thing. So in that case, x will be here. So for first case, it is x1 only. For second case, x2 minus x1. So x2, x1, x2, x3 are here, but the coefficients will be here in the design matrix. Similarly, for the third observation, it is 0 minus 1a means x3 minus x2. Oh, no, something is wrong. You can see it is wrong here.
So third and fourth.
Sir, it will be
both
1.
are- So third and
Fourth
fourth
is
both
okay.
are wrong.
Fourth is okay. Fifth is okay.
Nice.
Third one is wrong.
Third element.
Yes, it should
One.
be x3 minus x2.
One
So
also.
it will be minus 1 and it should be
1.
1. Yes. Okay. So it is wrong here. Is it correct now?
Yes, sir.
Okay. Now we will see for weight matrix. So weight matrix, you must have studied about weight matrix. It uses the values, inverse values of what?
Cofactor matrix.
In the here case, we can use the variance. In the question, you can see here. You can see the standard deviation of an observed height difference can be determined using 0.005 under root k. So standard deviation is given. We can compute sigma from here. Yeah, it is sigma. For every observation, we can compute sigma from here. Then we can go for sigma square, and then we can take its inverse. So at the end, what we will get? We will get the weight matrix. So everyone, please look at the weight matrix. Ruchi. Ruchi, can you hear me?
Yes, sir. Hello.
Please explain how we have prepared this weight matrix. Did you get it?
Yes, sir.
Can you explain it? If you cannot, just say no. Sumit.
Sir.
Sumit.
Yes, sir. Sir, we have taken inverse of the sigma square, and sigma square we have calculated from the given function, that is 0.005 under root k.
Good, very good. Alok, it is clear to you?
Yes, sir.
Praveen.
Yes, sir.
Please explain once again.
Sir, this is value of sigma 11 square
Mhm. Try to explain.
सर सिग्मा 1 की स्क्वायर जो होता है उसकी वैल्यू पे पुट कर रही है 1/008.2 और सर यहाँ पे जो फर्दर
Explain in this way, like the elements of the weight matrix are inverse of the variance. Okay, inverse of the cofactor matrix elements, whatever you want to say. So in this case, we are having the standard deviation. It is sigma. Then to compute the variance, we can go for the square. And to compute the weight matrix, we will take inverse of it. Now is it clear to you?
yes, sir.
So now you can see we have created our design matrix. It is A. We have weight matrix. It is P. L is missing. So L is given in your table. Okay. So using this A, P, and L, we can compute our the estimates of the adjusted heights. So we are having A, P, and L. So N is ATPA. So you can compute N inverse here. U1 is ATPW. W is here as a residual. Suppose it should be very clear to you. If I am using here at the place of W1, if I'm using ATPL directly observations, I will get the adjusted heights. If I am using the approximate residual W1 here, then I will get the residuals which I have to add in the actual observations. So for this case, you can see here U1 is ATP1 W1, and you are very sure that what was W1? It was disclosure F1 X0 minus L1. So if I am putting W1 here in the equation, then what I have to do after getting the estimates, I have to add it with our initial, means approximate heights. If I am using directly the observations, I will get the adjusted estimates here. Is it clear to everyone? Sumit?
Yes, sir. Clear, sir.
Is it clear to you?
Yes, sir.
Whatever questions you all have solved earlier in the classes, it was like U1 equal to ATPL, isn't it? So at the place of L, if we are putting the value of misclosure, means you are putting here the residual, whatever approximate residual. So in that case, whatever estimates you will get, it will be a residual. So that residual you have to add in the initial heights, or you can say approximate heights. If I am putting directly the observations L1, L2, L3, L4 at the place of W, whatever, this is what you do in your, you have done in the earlier classes. Then you have not to add anything. Whatever you will get as this in the third line delta, it will be the estimate, your estimates. So this will be the estimates of the adjusted heights. If I am putting W1 using it as a misclosure, then I will get the residuals which I have to add after this calculation. And if you want to calculate the cofactor matrix, posteriori variance factor, and covariance matrix, you know the expressions. It is QX and CX. So the final answer you will get after completing the first part, it will be the adjusted heights. It is 276.359 to 93.354 to 68.308, and standard error 0.0064, 0.067, 0.07. I'll share this presentation to you all, and you have to check it. Try to put L here and try to put W1 and see the answers. Okay. So is it clear to everyone?
Yes, sir.
Any doubts on that?
Sir, please turn that previous slide.
Yes.
सर इसको मैटलैब में कैसे करेंगे?
In MATLAB, you have to make the equations by yourself.
Sir, please can you explain the third one, sir, misclosure and design matrix, how those values have come?
In misclosure, it is f1 x naught minus L1. Okay. So f1 x naught is this, x1 naught, x2 naught, x3 naught. Or what you can, once again, what you can do, look at here.
Yes, sir.
So
Yes, sir.
f1 x naught minus L1. Okay. So
Yes, sir.
f1 x naught. So in your case, it is linear. So x1 naught is 276.358.
Yes, sir. Yes, sir.
Means you are sending this L1 to that side. Okay.
Okay,
You are
sir.
sending this L1 to that side. So it will be x1 value, you know, from here x1 naught minus 14.88 minus L1. It should be 0. If all values are correct, there is, if it is 0, it means there is no misclosure. Everything is okay.
Sir, then how we will be getting the L1 cap value, sir?
L1 is observation.
Sir, L1 is observation, and sir, fx naught is this value which is being under the heading approximate heights, and sir, L1 which we have been given the height difference.
Yes.
Sir,
Look at the table.
yes, sir. Sir, then how those value will come 0, sir? That is a little bit confusing to me, sir.
Try to put all these there. How we are doing? Just think. We are just taking the value which we are given to 14.88. Okay.
Yes.
And we are adding this value, the observed height difference, and we are reaching to x1. And but
Yes.
we know that it is not the actual height. Actual
Yes,
height
sir.
will be a little different. That's why we are saying it approximate height, or we can see it initial value, initial known value of the height.
Yes, sir.
On the basis of this value, it may be different. No, it will not be constant always. It may be different. As per the equations, it will be changing. So
Sir,
it's not a
till
problem. It may be value, but yes.
sir, till point of x1, x2, x3, I got understood, sir. Sir, but when we are calculating that fourth one, that where we are forming the matrix, approximate matrix, sir, that point 0, how 0 is coming, sir? That is not I'm getting understood.
In case of L4, it is not 0.
So there is 0, comma 0, comma 0, something is given, sir.
For first 3, it is 0.
So that only I'm asking how 0 is coming, sir.
Because these values are calculated using the height differences. You must think, see one thing. Look at the delta 1. This one. Is it 0?
Yes, sir.
Is it 0?
No, sir.
As
No,
per
sir.
that equation, if you are thinking like if there is 0, 0 and 0, so you should get delta 1, it should be 0 then again.
Yes, sir.
Isn't it?
Yes, sir.
That is not affecting the whole equation, because it should not be 0. In practically, it should not be 0. But as we are calculating our approximate height using the same height difference which was given in the observations, then it
Yes,
will
sir.
be 0, as we have made the equations. Here you can see. When you are computing this x1 naught, x2 naught, and x3 naught, for that cases we have used directly the height differences. But we know this is not the actual height. So because using the suppose using the L1, L2, and which one, L3 or L4, we have calculated the x1, x2, and x3. Okay, and we have taken the observations. We can see in the tables also. So that will be different because observations may be taken for the same type of things. Suppose HA minus H1 is taken 3 times. So it will be different all the time. It will be very slight. It may be 0.0001, but it will be different. It depends on the instrument. So it is not an issue for us because we have defined x1, x2, and x3 using the simple equations. So that's why it is we are getting it 0 as 0 and 0. Is it clear to you?
Yes, sir.
Do
Now
one thing. Do one thing. Once you calculate the delta 1, the final adjusted heights, okay, put these height. Put the one second, where it is. So these are your adjusted heights, okay.
yes, sir.
If you want to get the actual misclosure, that was not actual. If you want to get the actual one, then you have to put these 3 adjusted heights here in these equations. Then you will get the actual misclosure. It is not the actual one. It is on the basis of approximate heights, and it will definitely change.
Okay.
Is it clear now?
Yes, sir.
Okay. Is there any doubt regarding this question? Anyone?
Sir, how do you calculate priori variance matrix? Sigma naught square.
Which one?
Sir, I think you have presented it by S naught.
S not here.
Huh.
It's just VTPV upon n minus u. This formula you have seen in your book, in your copy, or Ramji sir has shown you how they have derived or how it is defined.
Sir, this is a post priori matrix, na?
Hmm.
I am asking about priori variance matrix. Sigma naught square.
Sigma naught square, where we are using that?
I think so. Sigma sigma xx is equal to sigma naught square into qxx. मतलब cofactor matrix into, I think it is reference matrix.
Reference value, sigma naught square.
So that was given in question, sir.
If it is given, then you will use.
Otherwise, we take one.
Hmm.
Okay, sir. Thank you.
Okay. But in this case, it was not given. And we have not used that also. Okay. So is everything okay till here?
Yes, sir.
Okay.
Yes, sir.
Now let's see the second question. What is was? Now, if at later date the height difference from 1 to 3 is observed to be minus 8.070. So height difference from 1 to 3 means x3 minus x1. Okay. And its length is 22 kilometer. Determine new sets of least squares estimates and standard deviations of points 1 to 3 using sequential parametric least square method. Okay. So now we are having the next set of observation, and here it is one observation. So how you will proceed? So let's talk about sequential least square here, because if you are getting the observations in sequence by sequence, in that case you need to use the sequential least square. So what is the need when all the measurements are not available in a single batch? Suppose we are taking the observations in real time. So we have to take the observation, you have to process, you have to take the observation, you have to process. So in these scenarios, we may use sequential least square. So how you get the result in this processing? The parameters are updated sequentially as new observations are available. So how we are thinking that new observations are coming, we are processing it, we are getting the corrections, and we are updating the previous value. Previously, we were having the estimated x1 cap. Next time, when you got the new observations, you process it, and you got delta x. So the x2 will be x1 plus delta x. So we have to compute that delta x. So you can see x1 was previous estimate. Okay, delta x you have to compute on the basis of new observations, and you got the next updated estimate. Similarly, we are thinking about the covariance matrix, cx equal to cx1 plus delta cx1. So the whole objective, our objective will be to compute delta x and delta c on the basis of new observations. Once we have done that, then directly we can compute x and c. So what is the advantage? Provide identical results to combined observation adjustment, which is expensive. So we know if you are taking all the observations at time, and especially in the real time case, when the matrix size will be increasing in every second. So for that case, if because that will be very computationally expensive, so for that case, it will be advantageous to use sequential least square. So let's see what are the steps. So we have batch one observations, number of observations, and one its design matrix A1, W1, disclosure, P1 weight matrix for that observation set means batch one, X not initial heights of approximate heights, and delta one the adjusted one. So initial adjustment was delta one equal to minus n inverse 1 U1. So at the next time when you are having the next observations, new observation, it is batch 2. It will be L2 equal to fx2, something kind of function. We will be having n2 a number of observations, and we'll be having the information of weights like P2. So how we can think? We can simply write the equation L1 equal to fx1. We can write L1 plus U1 equal to f1 x0 is the initial approximate heights plus delta f1. You have seen this equation. Similarly, we can write the second equation L2 equal to fx2. So if we write this equation, you can write A1 delta means A1x on using these equations. Using W1 minus V1. So you know about A1, it is made from Jacobian matrix, it is the design matrix. And what is W1? W1 is the here given here F1 x0 minus L1. This F1 x0 will be a constant, L1 be a constant or a single column matrix. So its difference will be the W1 here. As you have seen this equation here when we are calculating the misclosure, these things. So A1 delta plus W1 minus A1 equal to 0 means we have the residual, we have the misclosure, and we have the A1 delta. So all these things when we add, it will be 0. Similarly for the second case. So now what will be the function? As you have seen in the least square case, it was VT PV should be minimum like that. So for this case, the criteria should be like this. So VT PV for the first one, V2 PV P2 T P2 V2 for the second case, and these are the constants. What we call is Lagrangian constant, something like that. So this function should be minimum for our case. I'm not going to solve it. So what would be the answer? What we are expecting for the user when we have used the new observations, it will be delta 2. So the previous estimate is delta 1 plus this one delta. Similarly for covariance matrix, it is qx2 equal to qx1 plus delta qx1. And what would be this delta? So this value you can compute n inverse a to t m. So this expression you have to see. So what will be the objective once you have new observations? You have to just focus on to compute this one. If you have this value, you can directly put it here and you can compute the delta 2. Similarly, if you have this value delta q, you can put this value here and you can compute the qx2. So once you are when your objective is to solve the question, you are looking at any question, any problem, you have to just think how I can compute this one. and this one. Okay, if anyone want its derivation, I have to see the literature, then I can share it to you if you wanna. But if you are solving the question, you have to just focus on this line. Okay, if you look at the next one, the part B, what was the question? Now at the later date, the height difference from 1 to 3 is observed to be minus 8.070. So for this case, you have to compute the least square estimates and standard deviations for points 1, 2, and 3. So you have to see just at these equations. For the new case, when you are having a new observation, it will be like L6 equal to x3 minus x2 because the height difference was given between 3 and 1. If you calculate the approximate height, you can it is the same because x1, x2, and x3 from the same equation. You can compute the missed closure for the this new single observation. It is LW2 equal to F2x0 minus L2 A2. Similarly, you can see here it is x3 and x1, x3 and minus x1. So for x1 it is minus 1, and for x3 the coefficient will be 1. You can compute the weight matrix. It was given to you. The k is 22 kilometer here. It is given here. Okay. We have P2 now, Q2 now. Now you have to just use these equations of sequential least square. They are computing m on the basis of this correction value, and this correction value is then applied here. Once it is applied, we have previous estimates, we have to add, and we will get the new estimate on the basis of new observation. Similarly, we will do for the covariance matrix. Now you can see a cofactor matrix. Similarly, you can see I can calculate the delta V1, the corrections to observation residuals. So initially we are having the V1 residual, then it will be corrected by delta V1, and we can compute the new corrected residuals V2. Because as the observations will increase, your estimates will means observation will increase, your estimates will change, and as it is changing, your residual will be changing. So similarly for our case, if when you are including a new observation, then S0 square value will change, and the covariance matrix will be computed like this. Because you are having the QX2 value, so directly you can compute CX here. So these will be the actual means finally after including the next observation, this will be the answer. So I will share this presentation to you all, and you have to try to compute, and you have to get these answers. Okay, these are the examples of a book. I found it it was very good example, so that's why I have taken this. So you have to try to solve each step, and you have to get this answer. Okay. So any doubt regarding this? Alok, Sumit, anyone? Any doubt on this?
No, sir.
Shivam? Shivam?
Hello.
Yes, Shivam. Any doubt?
After we दोबारा repeat करेंगे
Your voice is not clear.
Hello.
Your voice is not clear. Rahul?
Yes, sir.
Is it clear to you?
Yes, sir.
Okay. So it was about sequential least square. I will share this. Okay. So try to solve these questions.
Okay, sir.
Okay, now we will discuss about Kalman filter. So take a break of 5 minutes and then we'll start. Okay. So shall we start? So shall we start now?
Yes, sir.
Okay. So now we will talk about Kalman filter. Okay. So let's see a comparison. When you talk about least squares, so it was the first technique to estimate parameters from the erroneous measurements. It was proposed by Carl Friedrich Gauss in 1795. And what is the objective? The least square aims to minimize the residual of the observation. It is V. But if we talk about the Kalman filter, it is the modified least square estimation method, and it is a recursive one. Means it works in a loop. Second thing, it aims to minimize not the residual. It aims to minimize mean square observation. So the both are having different objectives. Least square is trying to minimize the residual of observation, where Kalman filter is trying to minimize the mean square error of the solution. So if you look at the least square, it will process all the observations at a time, and it cannot be used to address dynamic events, means events that are changing with the time. But in case of Kalman filter, you can attempt many observations at a time, and you can work in at time basis at T1, at T2, and T3. You can process it recursively, and you can include dynamic characteristics also. Like suppose you are talking about the deformation, so how it is deforming, how its position, velocity changing, and you can also include about the force which is behind this. So whenever you are talking about the dynamic events, it is like if you're talking about the deformation, it will be the force, it will be the stress or shear that will be forcing that body or surface to deform. Okay. So how we can define the Kalman filter? It is an optimal recursive data processing algorithm which incorporates all available information regardless of the precision. Means it will not see what is the precision of any observation. It will include all the observations. Typical example of the Kalman filter you can see here. Suppose there is a system which is having some control inputs. It is having some error sources. So when using this system, and we are having some measuring device, and we are having some measurements which is having errors. So once these measurements will be fed to the Kalman filter, these observed measurements will be fed to the Kalman filter, the output will be the optimal. In sense of we are trying to minimize the mean square error. So we can see here the basic equations for the Kalman filters are system and observation equations. So this is the system and observation equations. System equation can be shown like this: xk equal to 5k xk bk uk plus wk. And observation equations you have seen: zk equal to hk xk plus vk. The zk is the observation matrix. You can see here the zk. It was lk in your case. This is the design matrix hk. In your case it was ak. Xk was the same, and vk is the residual. So the names are different for here. We can see one by one. So first of all, this xk. What is this xk? So this xk is called a state vector, and we know this xk is will contain the parameters which you have to estimate. So we can see here state vector at time k containing coordinates, velocities, accelerations, or anything whatever you want to compute. So this is xk. If you look at the uk, it is the control input of the system. It will be deterministic. If you use the look at the wk, so it is a system equation. So this is a term which is added as the system noise. And what will be the xk plus 1? Xk was the state vector at k time, and xk plus 1 will be the state vector at time k plus 1. Means we are talking about the next step. So in this case, at time xk, we were having the position, velocity, and acceleration at time k. But xk plus 1, it will be the coordinate, velocity, and position, velocity, and acceleration at time k plus 1. Means we are trying to update the equation. And that's why this phi k is called STM, straight transition matrix. Means using the information of kth time, xk, uk, wk, we are trying to compute the information at k plus 1. So it is a straight transition matrix, phi k. If we look at the next question, it is zk is the observation matrix. Sk design matrix, you know about it. Sk is the same. And this is the observation matrix, that will be the residual, or you can say measurement noise. Okay. Whatever measurements you are having, it is the measurement noise. So in the typical Kalman filter, we are having the assumptions to make it to give the optimal solutions. So what are these assumptions? Assumptions are that the system noise and measurement noise will be the mean of these noises will be 0. This is first assumption. And second assumption that both the noises will be white noise. White noise means You can see here it is 0 and it is 0. Means noise at time k will not be related or correlated with noise at any epoch. Means noise at time tk will not be related with dependent, or you can say will not be correlated with noise at time tk plus 1, and it will not vk will not be dependent on wk anyhow, and wk will not be correlated with vk anyhow. So it means white noise, and white noise means this should be 0 in covariance matrix. So for cofact, you can say here the try to say covariance matrix. So for the wk covariance matrix is qk, and for vk means for the observation matrix, observation equation, the covariance matrix is rk. So these things you have to take care of. So vk is measurement noise, wk is system noise having the mean 0. This is a covariance matrix of system noise, and this is the covariance matrix of measurement noise. So on the basis of these equations, I will show you what are the main equations of Kalman filter. Okay, so Kalman filter works in 2 steps. First one is time update, and second one is measurement update. The time update equations are called prediction equations, and measurement update equations are called correction equations. That's why sometimes we call it predictor corrector type algorithm to Kalman filter. So in the first step, what it will try to predict the any measurement. Suppose we are having the measurement at T1, and you are trying to compute the measurement at T2. Okay, so in the first step, we'll be trying to do that, and we'll predict. We are standing at T1 and we are trying to predict the value of T2. And this was the time update equation. And second was the measurement update equation. What we will do, whatever we have predicted at T2, we will try to correct it using the actual observations observed at T2. Means first time we are predicting any value, and second time we are correcting it, giving some corrections on the basis of observations that were observed at that time. You can see from here. Suppose we are having some initial values, and I have written is xk by k, pk by k. Okay, so it is the mean and covariance value. So what it means, k by k means we are having the value at k, and we have used the observations of time k here. It is a little confusing. Yes, xk by k means we are this is the estimate at time k using the observation of k. This is the covariance matrix at time k using the observations or measurements at time k. Means these are initial adjusted values or any initial value. So what you have to do first, we will try to predict it. So we will try to predict means we are trying to update it in time. Means we are going for time update equations. So what will be the value? We are talking about x value at k plus 1, but using the observations of k. So that's why we are saying it prediction. We are using the observations of that have been covered previously. We are not using any new observation. So on the basis of observations at k, we are trying to get the value of x at k plus 1, means at next epoch. Similarly for the covariance matrix. So how we are doing that? So these are your time update equations. Using the all values of k at time k, we are trying to calculate the values at k plus 1. Similarly for the covariance matrix. You can see right here equations. The covariance matrix will be written like phi k transpose, and if it is having no zero variance, then it will be removed. It will be like a constant here. It will be removed, and only qk will be there. So qk is the system. Yes, it is a system covariance matrix from system noise. Now, once we have predicted, now we will think of correcting it. So these are the values. Okay. Now we'll go for measurement update, means correction, and you can see here the notations. It is xk plus 1 slash k plus 1, means now it is the corrected value. Corrected will be shown like this, and predicted one will be shown like this. So observations, x value, adjusted x value at k plus 1 using the observations at k plus 1. Covariance matrix at k plus 1 using the observations or measurements at k plus 1. So we can see its equations also. So how we are doing this? We are taking the current step observation. This one. So once you have current step observation is zk plus 1, we will try to compute the Kalman gain. We will try to compute the innovation vector. Then we will update it, xk plus 1 by k plus 1 and pk plus 1 slash k plus 1. So this factor is called Kalman gain. This one is a priori covariance of the state vector. This is what I am saying here. A priori, it is the predicted one here. You can see here. And once we have applied the correction, we will say posteriori. We know HK is the design matrix. We know the RK is a covariance matrix of measurement noise. VK is actually the innovation vector. These are the crucial terms: innovation vector and Kalman gain in case of Kalman filter. Get k plus 1 is the observation matrix. Is again design matrix. Xk plus 1 by k a priori estimate of the state vector. This one. So you can see also here we have computed the Kalman gain, we have computed the innovation vector. Now we will multiply it, and this factor will be given as correction to the predicted value. This one is the predicted value. This one is the correction. And once we have done that, we will get the corrected value. It is the measurement update. Similarly for the covariance matrix. So once it is done, what will happen? Now these xk plus 1 by k plus 1 and pk plus 1 by k plus 1 will be fed to the time update equation. You can see here this is completing the loop. That's why I was calling it recursive. Using some initial values, it predicted. Then using some observation, it was corrected. Then corrected value was again fed to the time update equation for prediction. So suppose you are having 10 values at 10 epochs: T1, T2, T3, T4, T5, T6, T7, T8, T9, T10. Okay. So what you can do, T1, suppose you are giving a 00 value or T1 value as the initial values. So we have given T1 here. Okay. T1 values is given. Then what you are trying to predict, we are predicting T1 values. We are predicting values for the T2. This is prediction. Then we use the observation at T2, which was available with us. Observation at T2. Then we corrected our predicted value at T2. Now this will be the final value at T2. Then again it will be fed here as an initial value. Then it will predict for T3. Now again it will use the values at T3, and it will be corrected, and T3 will be given to time update for prediction of T4. So it is working in a loop. First value will be taken, prediction for second one, second will be corrected. So in this, what we are doing, we are just filtering the noise. Kalman filter, we are saying Kalman filter is. So we are filtering the noise. First thing. Second thing, what we can do, we can go for prediction. Suppose this was ninth correction. Then it was given for prediction for 10th value. Then using the 10th observation, we corrected our 10th observation. Then again we can predict for 11th one, which is not with us. Here we can predict for 11th epoch, T11. So what we can do, we can go for filtering also, noise filtering also. We can go for prediction of values also. if I'm having values T1 to T10, then I will try to predict for what will be the value at T11. So many of times Kalman filter has been used for prediction also. So you have to just see as these two set of equations, one prediction and one correction, and we have to just see what are the variables which I have to compute, like Kalman gain, innovation vector, or some initial values, how I can get that. Using these values, we can go for noise filtering, we can go for prediction using the Kalman filter. Any question on that?
So these are also solved by MATLAB.
Sorry?
Sir, these are also solved by MATLAB.
You can.
Okay.
Have I taught you the loops for while or do while?
No, sir. Only till if else.
After that, I have to talk about that. Let's see if I'm taking the tomorrow's lab now. Then I will tell you about how to use loops. Okay. So these are very simple. You can do it by yourself. Just search loops. The name of loops in your search box of the MATLAB window. Just write for like do while. Then it will give you the syntaxes how to use loops, and there will be examples also. You can learn it. Okay. Any question regarding the equations or the concept of the Kalman filter? Sumit?
No, sir. Sir means basically this filter is used for filtering the noise.
Yes,
Isn't
you
it?
can use it for filtering the noise and for prediction also.
Okay, means for prediction of the next observation. Okay, sir. Sir, this one current step observation. This, sir, in one word, what we can say what it does, sir. The current step observation, this process.
Simply think like that. We have the observation at T1 and T2. Okay. Using the observations of T1, first what we are doing, we are predicting the value of T2. Okay. After prediction, we have to correct that value, the predicted one. To correct that value, you are using the observations at T2. Okay.
Yes, sir.
So you can see here. This is your observation. Okay.
Yes, sir.
You can see ZK is your observation. You can see. So ZK plus 1 is your observation. We are taking the difference here. Observation, actual observation minus. This is actually the predicted observation. This is the what do you say, design matrix. Okay.
Okay.
You have seen this v equal to
Yes.
ax plus b kind of thing. So this is ax. So you can say predicted observation. So we are taking its difference, whatever is difference, that will be directly multiplied by Kalman gain, and that will be added to the predicted parameter state vector. So this value, this difference is directly here in this equation, that is directly affecting the actual corrected value.
Okay, sir. Sir,
Means
what does it stand for, sir? This S cap suffix k plus 1 oblique k plus 1. What does it mean, sir?
xk, we are calling it state vector. State vector will
Means
contain whatever.
this why this is written? No, what does it signifies? K plus 1 oblique k plus 1.
It is telling you like what value we have, what epoch it belongs to, and on the basis of what observations.
Okay, sir.
K plus 1 means we are talking about the values at k plus 1 If it is slash k, it means it has used the observations at k,
Okay.
means previous
Okay.
observations.
Yes, sir.
If it is k plus 1 by k plus 1, it means values at k plus 1 using
Why?
observations
Okay.
at k plus 1.
Okay, sir. Thank you, sir.
Okay. So let's look at a problem. Okay. Now you will get it. Just read the question. Consider a hypothetical train wagon that is capable of running smoothly on a perfectly frictionless long straight trail. Assume the initial state of a wagon is such that it was stationary at position 0, and when it is given a tap, it runs a constant speed with a random acceleration of 0.1 meter per second square. Okay. Answer the following filtering problem. Derive the Kalman filter dynamic and observation models for the current state of the wagon and what its velocity will be if the position of the wagon is measured at a later time delta t. It's just asking for the expression. It wants to calculate the position and velocity. Determine the optimal position and velocity of the wagon. It is the second one. If the position of the wagon was measured imprecisely at 50 meter with the standard deviation of 1 meter at delta t equal to 30 seconds. So it is telling about the initial state of the wagon. It was 0. After giving a tap, it was having a constant speed, but the random acceleration of 0.1 meter per second square. Okay. So it is asking first Kalman filter dynamic and observation models. Okay. So let's see. So what is asking? It is asking for the first equation, dynamic and observation models. So the whatever it is called in dynamic, it is the system equation here, and we have to get the observation equation ZK. So we have to search for these equations. This is what is required for the question 1a. Okay, so as we can see, it is talking about position velocity, and we know the simple equations of means position and velocity. Let's see. Simply, if you have to calculate the position at k plus 1, what you can write? Position at k plus vt plus half at square, isn't it? It's like that, na? X1 equal to x naught plus vt plus half at square. Simple motion equation. Is it clear?
Yes, sir.
So for our case, we have position at k, we have velocity at k, we know the time difference 1 by 2, we have the acceleration at k, delta t square plus WPK is the system noise for our equation. The equation for this noise for this equation, we're assuming it. And using this equation, we can compute the position at k plus 1. Similarly, if you want to calculate the velocity at k plus 1, you can write velocity at k plus means u plus at kind of thing, vk plus a delta t plus noise in that in this equation. So if you write it in the simple matrix equation, how you can write? Pk plus 1, vk plus 1, 1 delta t, and for this case there is no p, so 0. For vk, it is coefficient is 1, 1 plus for ak it is half delta t square, and for ak it is delta t, so half delta t square and delta t plus wk. Is it clear to everyone? These are very simple basic equations, and we are writing it in matrix form. You can see in the state vector what I have put. I have put the position velocity, which is required for our case. In the question, we have to provide the position velocity. That's why in the state vector I have put the position velocity. So is this equation is clear to everyone? Alok, Praveen, Sumit.
Yes, sir.
Yes, sir. My side clear, sir.
Okay. So this equation is very much equivalent to our system equation. You can see vk plus 1, vk plus 1 is the xk plus 1. Phi k is 1 delta t 0 1. Xk is pk vk. BK is this one, UK is this one, AK, and WK is WK. So now we have got the dynamic equation, whatever it was asking, the system equation. Similarly, we can see in the equation, it was talking about the position only. So what is our observation? Position only. So for that case, if you are using the XK, this one as XK, PK plus 1, VK plus 1, you have to write the equation. You can see here now one thing. It was XK, it was XK plus 1, but both will be having the same elements. So we have to write the equation in same form. XK is there, first write XK, PK, VK. And we can see the observation is only related to the position. So it will be the 1. There is no velocity, so 0 plus EK plus 1. So EK plus 1 is actually here the VK plus 1. So these are the simple dynamic and observation equations which we can write for our case. Any problem in that? If we have to work on the acceleration also, we may have included it here, but that is not required for our case. We have to work on the position and velocity only. That's why we in the state vector we have included position and velocity only. And we can see that there was a random acceleration point 0.1 meter per second square. So that will be used for our calculation of the system noise, covariance matrix of the system noise. So are these questions are clear to everyone? Any doubt on that? In the first question 1A, it was asked us to just give the dynamic and observation models, and we have prepared that equations. This one and this one. Naveen.
Yes, sir.
Everything okay?
Yes, sir.
Vishal.
Yes, sir.
Any doubt? Abhijit. Abhijit, any doubt? Abhijit Sonkar.
Yes, sir.
Any doubt?
No, sir.
Don't say like yes and no only, yeah, because I will be giving you some questions also. So if you're not getting it, just let me know. So look at the question 1B. So what is the question? Determine the optimal position and velocity. We have to calculate the position and velocity of the wagon if the position of the wagon was measured imprecisely as 50 meters. So as the observation we have position only. And what is the standard deviation? It is 1 meter. And what is the time? It is delta t equal to 30 seconds. So look at our equations. If you compare both the equations, so we can compute here the values of 5K, BK, XK, and ZK, HK. So let's extract these values. We can see the, so 5K was 1 delta T01. So now we know the value of delta T which is given in the equation 1B. It is 30. As the design matrix, we have 1, 0. It is clear. As the XKK, as it was told to you in the question 1A, it was step initially, it was stationary, so position was 0. And we are we are starting with the covariance matrix of 0. Now, so for the case of QK, I have told you like the coefficient BK, I means that part, that component will be used for the calculation of the system noise. So the expression for that is bk sigma a square dk. Sigma a was given the random acceleration 0.1. So what you will do, you have to compute the bk, and you can see here the bk expression. Expression for bk was half delta t square and delta t. It is here. So you can compute the qk also. And in the question, the standard deviation for one is given for the observation. So for the cofactor covariance matrix for the observation noise will be 1. So now we are having most of the parameters. Now we can think of the go for the time update and correction equations. So if you have to see on the time update, or you can see prediction equations, so you have to simply use these equations and put your values of xk and bk. So the prediction was 0, and prediction in the case as pk was 0, so the first thing was 0, but qk was this value, so it is here. So it was the first thing. Now we are having the initially predicted values. Now we will go for the correction. How we are thinking about correction, because we have the observation value of 50. Okay. Now using the expressions, we will first compute the Kalman gain, then innovation vector, and then on the basis of that we will compute the corrected values of position and covariance matrix. So you can see here the what will be the velocity and position. Sorry. And what will be the values of covariance matrix. So what you have to do, once you get this presentation, you have to solve all these questions. Okay, because if I'll be trying to solve this question in the class, then it will take all the time of the class. So that's why I have given the values here, and you have to solve this. So any doubt regarding this question? You can see, first of all, what we have done, we have made the observation equation, this one, and sorry, this was the observation equation, the lower one, and the first one was the system equation, or you can see the dynamic model. Then what we did, we took all the values which were required for time update equation and the correction equation, and we performed the calculation, and finally we found the velocity and acceleration with the covariance. So is it clear to everyone? Rahul?
Yes, sir. Clear.
Ruchi? Sudhir? Vishal?
Yes, sir. Clear, sir.
Okay, so the first one. Let's look at the second one. Okay, now read this question. Sunil Kumar,
Yes, sir.
please explain what is the problem. Sunil,
Yes, sir.
please read the question and explain what is the what is required in this question.
सर एक व्हीकल है जिसपे एक रेडियो एंटीना लगा है। वो सर ऑब्टेन एक्सीलरेशन से 0.3 मीटर पर सेकंड स्क्वायर प्लस माइनस 0.06 मीटर पर सेकंड स्क्वायर चल रही है। सर उसकी जो करंट पोजीशन और जो वेलोसिटी है सर वो 61 मीटर प्लस माइनस 2.5 मीटर एंड 4.1 मीटर पर सेकंड प्लस माइनस 0.4 मीटर पर सेकंड है। और ये सर व्हीकल जो वैल्यू है वो 10 सेकंड के इंटरवल पे सर मेजर करती है। तो वेलोसिटी ये सर क्लियर रिकर्शन पे सर वेलोसिटी क्या होगी?
प्रॉब्लम समझ में आया? Is this problem to clear to everyone? Do we have to use the same formula which we have written in the last question, or any different one?
Sir, I think in previous formula we have to replace k plus 1 to k. Then so k minus 1 will come at right hand side of the equation, and the data is given.
That we have to do, because last time the information we have written for xk and we were trying to get for xk plus 1. This time they have shown for k minus 1, and definitely we'll be doing for k. Okay, let's start. So we have to given the initial values, isn't it? And we have to given the covariance matrix. Okay. So we have to just make these two equations. Once we are having these two equations, we will get the values of xk, phi k, bk. Then we will calculate wk also. We'll be having the values of zk, hk. So in this way, we will calculate all these things and we can go for prediction or correction. Okay. So let's see. We'll be doing all the things in the same way. The position equation will be like this, velocity equation will be like this, and we can make the system equation pk plus 1 vk plus 1 same equation is there. So it is equivalent to that equation, and we can extract the values of phi k, xk, bk, uk. In this case, you can see two things are given. So two observations are given. First one is the position, second one is velocity. So in the last case, only position was given. So you can see the equation was like 1 0, only 1 0. But in this case, we have two observations. One is for velocity, second is one is for position, second one is for velocity. So we can make this equation like this. Okay. So pk, vk plus 1 is the same. Xk is same, but this ak, the design matrix, which we have written here as hk, it will be changing. So now this equation is equivalent to the observation equation, so we can extract the required values. So we have extracted the phi k, bk, and hk. We are given the initial values xk by k, qxk. We can compute the noise matrix, covariance matrix for the system noise. It is given here, and now we can see in the last case it was rk plus 1 equal to 1. Because it was given for the single observation, it was the single value 1. But for this case, we are having two observation, and for both the standard deviation is given, isn't it? We can see in the equation. Yes, we can see here the mean value and the standard deviation, the mean value and the standard deviation. So that will be used for RK. RK is the observation covariance matrix from the observation noise. Okay. So now we have QK and RK. Now we can think of go for prediction correction. One more difference you can see here. This time xk plus 1 by k equal to phi k xkk plus bk uk. But last time you can see there was no information of bk uk. Only bk was there. But why we have written 0 0 here? We know xkk was 0, so it becomes 0. But bk uk, if you look at the question, so where's the question? Yes, you can see what was that? With a random acceleration of 0.1. Okay, so this random has taken here as mean 0. When it is taken as mean 0, so in this equation, this pk, this uk, because you are taking here as estimate. Suppose we are taking it as a mean, so mean of a random thing will be 0. Okay, so that's why the whole thing was 0. But in the next case, in this question, if we are looking at, you can see where is the problem. So you can see, yes, in the question it was given constant acceleration. It was having some value 0.3 and then 0. And in the last case it was random. So for this case there will be some value of bk uk which will be added to the equation. So that's why here phi k xk will be there, because xk is not it's non-zero matrix here, and bk uk is also is non-zero, so that will be non-zero. So we have calculated the xk by p and pk. This is the time update equations, or you can say prediction. Now we have to compute the Kalman gain, vk. We are having the observation now. Zk is not written here, but as you know, position velocities values are given. So on the basis of that, you will correct the you will calculate the position velocity for this case. So this is the corrected state vector. This is the corrected covariance matrix. So these are the final results. Okay. So kth. So for kth recursion, you can see here. Sorry. So this question is very similar to the last one. You also have to solve this. Now let's look at question 2b. It is continuing from the above answers and using the state vector measurements and their corresponding time steps at 10-second intervals. In table below, provide a summary of the values of the filtered state variables and corresponding standard deviations. Means now they are asking for what are the values that you are getting after correcting or predicting. They want to see this, and assuming uniform standard deviation of 2.5 meter and 0.5 meter per second for the position and velocity. So standard deviation is given here for the position and velocity. So at every 10, 20, 30, 40, 50 and 60, whatever the position measurements are given here, and their velocity measurements are also given here. The standard deviation is also given here. So now we are having the equation, just we have to think how to incorporate. So we'll be going in the same manner. How we'll be doing? Suppose we'll be predicting the value of for at 10 second, and they will be getting the using the observation, and we will be correcting our value for 10 second. They will predict and correct for the 20 second. Then we'll predict for and correct for 30 second. They will predict and correct for the 40 seconds. Similarly, we will predict and correct for the 50 second. Means we'll be working in a loop and we'll be predicting and correcting always. These are the equations. We go for time update, means prediction. Then we'll go for the corrections on the basis of actual values which were given in the table. So we can see here. So for the position, when you solve that question, what you will get for these time steps, these will be the predicted values and they will be the predicted standard deviations. Once using the actual observations, you are going for filtering, then this will be the filtered position and this will be the standard deviation. Similarly for velocities, you can see the predicted velocity, predicted standard deviation, filtered velocity and filtered standard deviation. You can see in the plot also for position. So the actual one, this diamond shape one, this was the measured one. The square box one was the predicted one, and this triangle line was the filtered one. So you can see how much far it is the prediction line, and after correction it is very much close to the measured values. Similarly for velocity, you can see this was the actual measured velocities. These are the filtered, sorry, these are the predicted one, and these are the measured. So measured, filtered and predicted one. So this is how you have to do the correction, prediction, correction, prediction, correction. Okay. So I will not explain this question. You have to do it by yourself. If you are facing any issue, just let me know. It is very similar to the first and second question, and you have to do it by yourself. So let me know if you are having any doubt regarding Kalman filter or any problem which I have explained question 1 and 2.
So please open example number 1.
Yes.
Sir, next slide. Sir, next. हाँ सर, ये सिग्मा ए स्क्वायर की वैल्यू 0.1 कैसे आ रही है? मतलब 1 स्टैंडर्ड डेविएशन 1 मीटर दे रखा है.
Now, this is for acceleration. 1 meter was given for position.
Oh, so okay, sir.
Okay.
Yes, sir. Get it.
Okay. Any other doubt?
No, sir.
Okay. Let me see. I can share from here or not. Okay, I will share this presentation to Sumit, and he will share it to you all. Okay.
Okay, sir.
Okay, so this class was about sequential least square Kalman filter. I have discussed 1 to 2 problems for each. So try to solve questions if you get somewhere, and let me know if you are having any doubt regarding that. Okay. Okay, so the class is over now.
Thank you, sir.
Thanks, sir.
Thank you, sir.